In this example, we're going to consider a structure which is a curved thin quarter of a ring and a straight segment of length L. I'm going to apply a load F horizontally at the end of this thing. Ignore this scribbling right over here. And I'm going to ask for the deflection caused by this load in the direction of this load. And the energies I'm going to use will be axial compression here, and there is no bending here. And then I'm going to use bending here, which predominates. We could almost certainly leave this term off, but I went ahead and included it anyway. And so, because we already have a load at the point where we want to calculate the deflection, that load's in the direction of the deflection, then we don't need a dummy load. I will be measuring my all locations from the right hand side and looking toward this right hand side, which means I don't have to do the statics for this reaction right here in this cantilevered problem. And so I need to write deflections due to the axial piece of this one, which means I need to write the axial load in this section, which is going to be a constant. And then I need to write the bending moment in this cross section, and that will depend on an angle theta. I forgot to label theta, but theta is measured from where the hand is. That's the angle theta, so theta starts out at 0 for vertical. Dealing with the axial piece first, the axial piece says the deflection due to axial only is an integral over the length of the straight piece times the compressive load times the partial of that compressive load with respect to my applied load F dx over AE. And my compressive load in this region, varying with the variable x, is a constant, and it's just F, which means my partial is a 1. So my deflection piece in this region is an integral of my load times the partial of the load with respect to x dx over AE, integrated over the entire length. And the F and the AE are constants. I can bring those out. This leaves an integral of 1 dx, which becomes the value of x, evaluated between 0 and L, just becomes L. So our deflection of this straight piece due to compression is FL over AE, our familiar axial compression deflection formula. Now we're going to turn to the second piece, and that's bending in the round section. And we need to, in this round section, we need to write the bending moment everywhere that's caused by the load F that was applied out there at the end of the straight section, but nothing changes with the moment. If I move the straight section force to right here, I still get the same moment. And so my moment as a function of theta is equal to the value of the force times the distance from the force to the point that I want to calculate out. And here's my hand is at the point where I want to calculate my bending moment, and my moment arm is shown here. It's a distance measured perpendicular to the force. Notice I've got a right triangle here of size r here, okay, and my distance I'm measuring is outside that right triangle. There's that 1 minus cosine of theta term again. If this distance is r, this little distance right here is r cosine of theta. This big distance is r. So this arm distance right here is big R minus r cosine of theta, or r times 1 minus cosine of theta. So my moment anywhere in that beam as a function of theta is the load F times the moment arm, r times 1 minus cosine of theta. The partial of my bending moment with respect to F is equal to r1 minus cosine of theta. Now my deflection piece due to bending of the circular ring, with the circular ring going 90 degrees, or from 0 to pi over 2, is the moment FR1 minus cosine of theta multiplied by the partial r times 1 minus cosine of theta. That means r will be squared and 1 minus cosine of theta will be squared, replacing dx with r d theta for these round problems, dividing by EI. This gives me my second deflection piece, and actually this will be the predominant deflection piece. Noticing that the F's, the R's, the E's, and the I's, all of those things are constants with respect to theta, so we can pull them outside of the integral. We're left with a 1 minus cosine theta squared, and 1 minus cosine theta squared can be expanded using FOIL into this term, and then we can integrate the 1, get a theta. Integrate the 2 cosine of theta, get a minus 2 sine of theta. And the integral of a cosine squared theta is theta over 2 plus sine of 2 theta over 4. We saw that in a previous problem. And we have to evaluate each of these theta terms at the limits as theta goes from 0 to pi over 2. And so that will give me the FR cubed over EI term. And theta between the limits of pi over 2 and 0 is pi over 2. Minus 2 sine of theta between the limits is a minus 2. Our theta over 2 at pi over 2 is a pi over 4. And the sine of 2 theta, both at 2 pi over 2, which is pi, and at 0, goes to 0. So that term evaluates to 0. And so my deflection piece, because of bending, is an FR cubed over EI times 3 pi over 4 minus 2. My total deflection would be the sum of delta 1 from here and delta 2 from here. And if we in fact plugged in numbers, we would see that this delta 2 term seriously outweighs this delta 1 term. And that would be the predominant deflection term.